right, hi everyone. Welcome to day 3 of the R Bootcamp. Today we're going to be talking about plotting for the most part, but before we get into what I had planned, I wanted to wrap up some things we talked about at the end of the last lecture, where I was asked a relatively simple question, and I just kind of got a little flustered. So I was. Did you guys get a chance to look at this at all? Okay. We were looking at this Lego data set, which is a data set of all of these Lego sets produced since 1970. And so I was asked how to summarize like the number of sets per year. And so I communicated with a couple students actually after class about other ways of doing this. And what was really hanging me up was, the kind of intuitive thing to do is you write a for loop and you go through the decades. And for each decade, you summarize something. In this case, it was just the sum of all the sets that had been produced in that decade. And so the question is really like how to go about doing that. So what got me confused, let's go into R. What got me confused was basically how to structure this which statement. So before I was talking about which is this function that just tells you the indexes of a logical vector that are true. So if you say like which true, false, true, this will return 1 and 3 as vector. So I wanted to kind of come up with a general solution that would return all of the rows of this particular data frame. So let me open up just this file with all of the code for this analysis. So we use read.csv to get this Lego data set, and we can take a look at it in RStudio just by clicking on it in our environment down here. So I made this table of all of the different of the number of sets produced each year, and then what I think about data in R in terms of the data being inside of a data frame. So that's another thing I got stuck on. So it's very easy to just turn this table into a data frame just by assigning these counts of sets as you can. In other words, you can turn this table into a vector by just using a function called asVector, and that will pull out all of these. Wait a second. Yeah, Lego. Here, sorry, I thought I did that before. There we go. So asVector will plot all of the counts as a numeric vector from this table, and the function names will pull out all of the years. So you can put that information into a data frame easily enough, and then it's kind of in a format that's easier to work with because you've got a column of years, a column of counts, and then I created a new data frame, this data frame Lego sets per decade, and this data frame just contains each decade, and the counts initialized to 0. That way we have somewhere to store the counts of Lego sets per decade that we're actually going to compute. So this is one solution, but I actually like this solution better, which I came up with after a student asked me a question over email. So to break down this line of code, you calculate, there are two major expressions here, which this line, Lego sets per year, and then $year pulls out the years from this data frame. So this has the number of sets for each individual year. And then using a logical comparison operator greater than or equal to, you can see if it's greater than or equal to D. D will iterate through, let's see, up here we assigned decades, so just the sequence from 1970 to 2010, each by 10, so each decade. So let me make sure to assign that. So when you're going through this for loop, we're saying so for D in decades. So that means the variable D is going to take on the value of each member of this vector decades. So we're not going to run through the whole for loop. I thought we'd just go through it. We just go through the first step to see how it works. So I'm going to explicitly assign this variable D the value 1970. So what you're saying here is that here are all the years from this data frame Lego sets per year, and so you're asking which of these are greater than or equal to D, which is 1970, and if that's the minimum year is 1971, so of course it's true for all of them. Then if you take a look at this expression, you're asking which of those years are less than D plus 10, so which of them are less than 1980, and that's only true for, of course, the ones that are less than 1979. So then, on the left-hand side of this, this is the vectorized logical AND operator, which just means that it works the same as the AND operator. So, you would say true and true. Notice this is the double ampersand. That will return true, or if it's false, it will return false. And we went through how that operator works. So how the vectorized AND operator works is that if you're comparing a single value like true to a vector of logical values, like let's say true and false, it will compare that single value to each value in the vector. So of course true and true is true, and then true and false is false. Do you guys see how that works? Are there any questions about anything else I've said? Okay. So if you give this vectorized comparison, logical AND operator two vectors to compare, so we'll call it false and false. This will print out a vector of just false and false. It will compare the first element of both vectors and then the second element of both vectors. So when we use this operator on these two larger logical vectors, what we really get back is just the second of these vectors. And the reason for that is because we're in the year 1970. So maybe I'll step through another year to kind of illustrate how this is going to change. Of course, that's just because the vector on the left-hand side of this operator is all true. So any vector you give to all true is going to return, is going to get you back the expression that has some false elements. So then, if we evaluate this whole expression inside of the which statement, this is the vector we get back, and then if we apply the function which to this vector, we'll get back the first 9 elements, which are the numbers 1 through 9, and that gives us the rows of this data frame Lego sets per year that we want to sum the counts for, the counts of the number of sets. So this expression does something similar. It just shows which, it determines which, so we're reading data from this data frame Lego sets per year, and then we're writing data to this data frame Lego sets per decade. So in order to calculate which row in the data frame Lego sets per decade that we're going to insert this value that we're calculating into, we see which of those rows is equal to the current decade that we're in, and then by using which, that will give us the actual row to insert into. So we use the sum function to just sum. So we've got a vector here that represents all of the counts of the number of sets over the years, and then we index that using a vector. The vector we're using to index it is rows, which we calculated before, and I stepped through that. It happens to be the integers of 1 through 9. So if we sum all those up and we evaluate that expression, we get 142, and then we store that in the row that we calculated from this variable insert row, and then just the second column, which we know we put it in the second column because that's where we're storing the counts. So we do that insertion, and then we go back to the beginning of the for loop, and we do it for 1980. Does that answer your question? And does anyone have any questions about this process or for loops or anything like that? Okay. And if you do, of course, we can come back. All right, so I just wanted to talk about that. So now we're going to do something that I think is exciting, which is to talk about plotting. R is known for the plots that you can create with R. Plotting in R is relatively easy compared to plotting other languages or just using other tools to plot. There are two main reasons for plots, and I'll kind of illustrate their usefulness and these reasons I really mean like the context of R. The first one is just explore a data set. And with R, you can create and destroy plots very quickly, and so you can find things out about a data set very quickly just by visualizing that data. And of course, the second way is to actually like communicate some idea that you're trying to get across to an individual or to an audience or to someone that you're working for. And R's plots are great for that, and we'll look into how to do that a little bit as well. So the plotting function that we'll start off with is plot. Plot and all of these plotting functions take huge numbers of arguments. So before we were talking about functions and what arguments they take and how to specify those arguments, plot easily can take like 100 arguments because that's the level of customization that R allows, but we're going to cover the basics. So in the simplest way you can use plot is to just give it a vector. So we'll give it a really simple vector, okay. So if you just give a numeric vector to plot and execute that line of code, you'll get back a plot, which, considering how little work you just did, is pretty decent. The vector that you gave it, the values in that vector are the y coordinates. The x coordinates are the index of that value in the vector. So here the index goes up to 5, but if we gave this another value, then it'll go up to 6. RStudio makes it very easy to save this plot or any other plots that you might make. If you just click export, you can do save as image or save as PDF, and you can specify how big you want it to be according to like how many pixels tall and wide you want it to be, and you can you can save it wherever you want on your computer. So that's really convenient. So let's get into plotting a little bit further. Let's see here. In my lecture notes for plotting, I created some fake data that I actually I like it a lot. It plays well, so I'm going to borrow that. So here I'm creating this data frame of completely fake information, but it's supposed to be average temperatures in Baltimore and Chicago, and then just like these arbitrary dates that these average temperatures correspond to. So we've made a very normal looking data frame with just columns of temperatures and also this date parameter. So if you want to specify, it's extremely possible that you might not just want to plot to plot a function, to plot a vector according to its index. So if you supply plot with two different vectors, and two arguments, then you can specify the x values and then the y values. So since we're looking at temperature over time, first we'll specify this vector of dates, and then we'll specify this vector of temperatures in Baltimore. And as you can see now, the x-axis has changed, so you can see the different dates, and the y-axis shows the temperature values, and the points are plotted according to their coordinates. So we can make this, we can sort of illustrate this information better. We can add label axes would be one thing that's nice. For label axes, you have to provide the argument names, but they're easy to remember. It's xlab and ylab. So we'll say xlab is equal to, and then you provide it with a string. So xlab is equal to date, and ylab we'll set equal to temperature, and that's easy enough to do. And now your plot is starting to make more sense. You can also add a title by specifying the main argument, and that's also a string. So I'm going to say average temperature over 10 days in Baltimore. And there you go. Does anyone have any questions about plotting so far? Or anything I've done? Okay, so as you can see, like you can start. It's not hard to plot, and you can start making figures that are decent looking pretty quickly. Since we're tracking changes in a continuous variable over time, instead of a scatter plot, you might want to make a line plot. So you can do that easily by specifying this argument of type, and you can set that equal to L. And then if you execute this line of code, now you've got a line plot, and that looks even better to me, at least. So let's say you wanted to, we have temperature data for two different cities. So let's say you wanted to show both on the same plot. The way that plotting works in R is that there are sort of these base plotting functions that plot something, that make an initial plot, and then there are other functions that add features to the plot and sort of add other layers to the plot. So if you wanted to draw another line on this plot, you'd use the function lines. Lines also takes dozens of arguments, but you can use it sort of in the same simple ways that you use the plot function. So if we give it the x coordinates of the dates and the y coordinates of the temperature in Chicago, and after executing this plot line of code, we execute lines, it'll draw the line. Now, of course, both lines are black, so there's no way to kind of tell the difference between these two changes. So in this as an argument to lines, if you specify a named argument call and set that equal to red, then if we execute both of these again, it'll draw a red line. And R understands most basic color words, so if you say blue, it'll draw a blue line or what have you. Of course, there's nothing on this figure to give any meaning to what these different colored lines actually mean. So we can use a function called legend, which adds a legend to this plot, which is adding another layer to this plot in the way that the lines function added another layer. The legend function is like a little tricky, so I'm actually going to get it from my notes and then explain to you what's going on. I don't think I copied it. The first, all right, so the first argument of legend is just, you can basically say top left, top right, bottom left, bottom right, and it will position the legend accordingly. Of course, when you depending on your data, you have to, you kind of have to place your legend according to your data. So it's not something that's easy to do programmatically. So if you're writing a function that just like automatically makes plots, you've got to put some thought into, if you're automatically generating legends, where to put that legend. So in the case of this plot, we've got a lot of room. We got some room in the bottom right and the bottom left. For some reason, bottom left worked for me. So then the next argument is a string of, is a vector of strings. And if we had multiple lines here, then we could specify more strings in this vector. But this just adds Baltimore and Chicago to the legend. This LTY argument just specifies the kind of line to draw next to the words Baltimore and Chicago. The call argument does something similar that it does in the lines function, except by giving it a vector, you're mapping the first element of this vector black to the word Baltimore as the first element of this vector. And in the same way, you're mapping red to Chicago. And then I used this inset argument to sort of push the legend up and to the right a little bit. So let me just execute this code, and I'll kind of show you what I mean. Each of these things. So that doesn't look very good, but when we blow this up, actually, it's looking good there. If we look at this, for some reason it came out better in the actual notes. At least I hope I did. I feel like it did. Yeah. I think this being huge is an artifact of some things I was playing around before. I was playing around with before when I was kind of experimenting with plotting options when I was figuring out what I was going to teach you guys. So if you execute this code and you haven't changed around those plotting options, it should show up like this. So now you've got a decent looking plot, a line plot for illustrating a basic data set here. Does anyone have any questions about that? Yeah.
What's the dollar sign doing?
Oh, sure. So the dollar sign is a way to get a column of a data frame as a vector by using the name of that column. So it's contingent on the fact that the column of the data frame has a name. So if I look at average temp, these are the column names of this data frame. Not all data frames have column names, in which case, the line of code average temp $ Baltimore is equivalent to average temp, and then indexing the column like a matrix, so just saying comma 1 and getting every row of the first column. Anyone else have any questions? Yeah.
Is there a way to find out some sort of like a general rule of parameters for functions? So, for example, legend, how we find out what's like the order of parameters that should be inserted?
Sure. So you can both of these work basically interchangeably. In the R console, you can write a question mark and the name of any function. So like question mark legend will give you all of the arguments to legend, which, as you can see, are not. Most of them most of them you can leave alone. But of course, you can customize plots in R like to your heart's content. So depending on what you want to do, you might need to change some of these. Also, and I was discussing this with another student during class last time. Sometimes question mark and the name of a function doesn't work depending on the function. So you can also use the function help and then write the name of the function that you want help on as a string, and that will bring up the same help page. No problem. Okay, so that's the basics of scatter plots and histograms in R. That's the basics of scattered plots and line plots in R. Now we're going to move on to histograms. Histograms are great for visualizing any kind of frequency or visualizing any any distribution of numbers. And we'll get more into that in next week's lecture when we talk about statistical functions and simulation. But the histogram function also potentially takes dozens of arguments, but in the same way, if you want to use it simply, you can. So you can specify a very you can provide just a numeric vector as an argument alone to the histogram function, and it'll work. So let's just make up some numbers. 2, 2. Let's see what this gets us. All right, so this gets us this histogram, which we've got frequency of the numbers in this vector on the y-axis, but these bars don't really tell us that much because this data set is small, and so it's hard. Of course, there are two elements in this vector between the number 1 and 4, and then between the number 4 and 6, there are 3 elements. Like that's fine, but there's a lot of power in quickly seeing distributions using the hist function, and so I want to pull in the data set I was using from our Lego data set, since that's kind of big enough to illustrate the hist function to the way that I want to talk about it. So we can load this into R. Okay, great. So here's our Lego set data set as a data frame. And so let's say I wanted to see the distribution of prices of sets. I could just say hist Legos and grab USD MSRP. So as you can see, this data set is highly skewed right. There are a couple. There are very few there are very few Lego sets that cost $600-800 and multiple hundreds of dollars. And then when you get down into this range, over 5,000 of them are seemingly less than $100 here. But if we want like a more, these bars are pretty big, especially considering the fact that the majority of this figure doesn't provide a lot of information. So if we wanted to make this histogram sort of more granular, we could specify the argument breaks, and I'm going to say breaks equals to 50, and let's see what that gets us. All right, so as you can see, I don't know how many breaks there were before, but it breaks up these bars so that each bar is smaller, and that better illustrates how right skewed the pricing of Legos is. That really most of the majority of them, over 4,000 of them, are sort of even left of say this is 100, so $50, $60, $70 is like somewhere around here. Does anyone have any questions about this? Okay. And with hist takes a lot of the arguments that plot also takes. So if you wanted to say, if you wanted to specify an x-axis label, you can say xlab dollars, and then you could specify the title by saying main is equal to prices of list, and that'll change things for you the same way it does with plot. Let me make sure that that's everything I wanted to say about histograms. Yeah, basically. Okay. Okay, so any questions on histograms? All right.
How do you change like the max of the x?
Sure, that's a good question. So, a great observation is that there's not a lot of information above $200. The thing I'm about to tell you also goes for the plot function. So you can. I know this works in plot. I'm hoping it works in histogram. If it doesn't, then I'll look it up. You can specify xlim, and in the same way, I don't know if you can do it with histograms, but in plot, you could specify ylim. And what you do is you give it a vector of two numbers. So let's say we want this to go from 0 to 250. I'm hoping this works. Yeah. Okay. So that shrunk our histogram down. We're throwing out all the data of all the Lego sets above $250, but it gives us a better look at where the bulk of Lego set pricing is. Let's see if you can use ylim. I don't know. That will make for a weird looking histogram. And I don't really recommend using ylim with histograms, but I'll show an example using plot. Oh yeah, I guess you can. So you can decapitate your histograms if you want. Like I said, I don't recommend that, but let me show an example of that with the plotting function. So we had our gorgeous plot of temperatures here, but if for some reason, if we wanted to, in this rendering of temperatures, it kind of looks like they're fluctuating a lot. And if we wanted to sort of change that perspective, we could specify a greater ylim. So instead of, right now it's between like 32 as the maximum and maybe this is whatever so 15 maybe. So we could say ylim is equal to c, and then it's a vector of two numbers, so we could say between 0 and 45. And that'll give us a much flatter looking lines because we're putting all this white space on top and on the bottom. Does that answer your question? Okay.
So, it seems like the order of the arguments doesn't really matter.
Yeah, so as long as the order of named arguments doesn't matter. So when I'm saying xlab equals, ylab equals, whenever I'm saying the name of the argument, the equal sign, and specifying a value, it doesn't matter. But these two arguments, it does matter because first I specify the x coordinates and then the y coordinates. If we look at the arguments for plot, it says to specify xy, even though really you only have to specify y if you just want the indexes on the x-axis. So plot is plot can become really complex if you want it to be. But in general, I recommend. In other words, sorry, what I'm really trying to say is that if you wanted to move these, and for whatever reason, it makes your code harder to read. So I don't recommend that. But if we specify this as x, if we say x equals that vector and y equals this vector, it should work. Let's see. Yeah, it works the same. Any other questions from that? Okay. Okay. Oh, sure.
Does the y-axis always show frequency?
So when you're using hist, yes. Okay. All right. So yeah. So I want to talk about the next plot I want to talk about is box plots. Box plots are, when I first encountered box plots in high school or middle school or something, they seem kind of arbitrary, but I hope that I'll be able to show you, especially next lecture, when we're talking about statistical functions and statistical distributions, that they're actually very useful, especially when exploring a data set or exploring any kind of data that's been generated from statistical functions, at identifying outliers and at kind of characterizing distributions in a different way than a histogram might help you characterize a distribution. So the box plot function is just called box plot. You can provide it with a single vector. Once again, box plot, these plotting functions get as complicated as you want, but if you give it a single vector, it'll plot you a perfectly wonderful box plot and show you, the mean, the interquartile range between the top and the bottom of the box, and then the maximum and the minimum of the data set. And if we included some crazy outlier like 50, hopefully we'll do it, it will shrink things down and plot 50 as a single point way out here in outer space. Now, box plot's a little bit different because you can provide it with several vectors, and it will plot box plots next to each other. So if I give it 3 vectors, it'll plot 3 box plots. I don't know when this will stop. I imagine there's some number where it'll say too many box plots in your figure. But this is a neat way to compare the distribution of different data sets. And we can, I can illustrate that better for you by working with this Lego data set again. So, let's do our favorite thing and divide this data set up into decades. So if we say Lego 70s, let's the way I really, let's say, so let's take a look at which data sets are, actually that would be interesting. Let's kind of cut up the Lego data set so that we've cut it up by the decade that the sets are in. So Lego 70s, I could say which Legos year is greater than or equal to 1970. And sorry, I'm getting nervous. This burned me last time. Legos years less than 80. Let's see what this gets me. Okay, good. And then these are the rows that I want. As a result of this vector, it gives me the indexes of the rows in the Lego data frame that I want. And so I can use the brackets to just take those rows out. And these are all the sets from the 70s. And actually, this will be richer if I use decades that have like more Lego sets in them. So let's do like less than 2020 and greater than 2010, please 20 or 10s. And then I'll get Legos from the 90s. Sorry. And then I'll get Legos from the aughts. Okay, let's make sure those look sensible. Yeah, great. Okay. Okay, so yeah, so then if I wanted to look at the distributions, if I wanted to see how prices are distributed between these different decades, I can just provide 3 different vectors to blocks plot. So I can say Lego 90s, USD MSRP, Lego 2000s, sorry. And yeah.
Why is there a comma here at the end of it?
You mean like this comma?
No, Legos which, Legos here.
Oh, okay. So what I'm doing is Legos is a data frame. And so you can index values out of a data frame using this like bracket and comma syntax. So if I wanted, if I wanted the first row, first column element, I could say 1, 1, and it will give me back that value. Yeah. So this expression gets us all of the rows from the 90s, and then we can just index them out with this syntax. Does everyone understand that? Okay. Yeah, so now, this is not a pretty graph, but this is how they're distributed. And the reason it's not pretty is because of all these outliers that, push these prices up into the multiple hundreds of dollars. If you're looking for an analysis, instead of your question might be, instead of your question being, sorry, let me slow down. If your question is how are the data sets, how are Lego set prices distributed across the decades, this plot doesn't give you a lot of information because the bulk of the sets are down here. However, if that's not your question, if your question is, if you're for some reason trying to analyze the outlier, the super expensive and exclusive Lego sets, this gives you a better, this gives you a sort of a better sense of the information, because you can see that there's a ceiling to how expensive Lego sets can be in the 90s, and as the decades go on, that gets broken. So if, depending on what information you're looking for, this might be exactly the plot you want to produce or kind of worthless to you. I'm not. Yeah.
I'm not entirely sure why you're using USD MSRP. Like, why are you using just not using like Lego 70s, Lego 80s, Lego 90s, just that much?
Oh, sure.
USD.
Sure. So this USD MSRP, this is just the column of prices. So like Lego 90s is, we just took out the block of rows from the overall data set that are from the 1990s. So by specifying, I have too many things. Did I answer your question? Okay.
Also, how do you, if you had to on the box plot, make the mean, like the value appear? How would you make that happen?
By the value, you mean like you?
It marks the value, but we can't find the exact value when you look at the plot because the range is so wide between 0 to 200.
Oh, so like you just mean how do we find the mean from this data set?
Yes.
Oh, okay.
Is there any way to plot the mean onto it?
Sure. So this is, I'm gonna try my best guess, and if not, we'll figure it out.
Yeah.
So the first thing I want to do is kind of lob off all of these outliers if that's not what we're interested in, and I think I can do that with ylim, but I'm not 100% sure. So let's see. So let's say like the maximum around here is 100. Okay, great. So now we can get a better sense of these. And so you want to plot, do you want to plot the mean for like a particular year? Okay, so again, my best guess of doing that. So you can draw arbitrary lines on plots in general using a function called abline. Abline again is another plotting function. It adds a layer. It has a bunch of arguments that have defaults, but you have to specify some of them. So to draw here we want to draw a horizontal line at the mean. Let's say the mean of the prices in the 90s. So this is getting into next lecture, but this is good because today's lecture and Wednesday's lecture actually really inform each other a lot. You can use the mean function. The mean function takes a numeric vector and finds the mean of that vector. So if we look at the Lego 90s, the Lego 90s data frame, we pull out USD MSRP. This might actually throw an error. Yes, it does. Okay. So there's missing data in this in this Legos 90 USD MSRP. Let me see if I can find one. Somewhere in here there's an NA, which represents a missing value, and that can throw these calculations off sometimes. So I think I can, yeah, if I go to mean and I specify this argument NARM, set that to true, that will pull out any NAs, and then that's the average price. So mean gets us the average price. We want to draw a horizontal line. So the four main arguments to abline are A, B. Go ahead. Sorry.
What does the NARM equal to true? Does that just make all the NAs 0?
So it pulls the NAs out.
Pulls them out.
So when you're doing the mean calculation, it makes the number of numbers smaller. Yeah, no, that's an important question. And dealing with missing data, if you're using R in a lab or professionally, is something you're definitely going to do. So abline has four main arguments, but you shouldn't specify all of them at once. You should either be specifying A and B, where you're specifying a straight linear line according to the function of A plus, y equals A plus bx. So A is the y-intercept, B is the slope. But we don't want to draw a line at an angle or a line with a slope. We want to draw a horizontal line. So you just specify h. So I'm going to say h is equal to this mean. Also, again, I don't know for sure this is going to work because I haven't drawn a lot of lines on scatter plots, but we'll see. So I say abline is equal to this mean, and let's give it a color. So I'm going to say col is equal to red. And there you go. Okay, well, it worked and it didn't work. I guess it worked. Oh, you know what? You know what the whole issue is? This is the problem. I said the wrong thing about scatter plots before. No, I didn't know. Why is it? Oh. All right. Well, now I'm confused about about what the.
We didn't change the line.
Oh, you're right. It is the median. That's what I thought. Sorry. Yes, it's okay. Before I misspoke, the black line is the median. Sorry about that. The black line is the median. The difference between the top and bottom of the box is the interquartile range, and then these bars are 1.5 times the interquartile range, and that's sort of the main. That's sort of the accepted canonical limit for whether or not something is an outlier. So sorry about that, and that's the case for all box plots. I'm sorry if I confused you. Here's the median. Yeah. So using abline is how you can draw that. If you I forgot. Does that answer your question? I forgot what I was going to say. Okay. So there are other details. There are other labeling details of box plots that we can get into, like if you want to add, we haven't even labeled what each of these individual box plots represents. So we can say, I think just names is equal to, and then give it a vector from, a vector of strings that maps to the arguments that we specified for drawing the box plots. So we can say 1990s, 2000s, 10s. Now label them, and then, like we did before, we can add a y-axis label with ylab, dollars, and we can add a title with main. So this is Legos. Okay, so that's the basics of box plots. Do you guys have any questions about that? Yeah.
The function of NA.rm.
So NA.rm is, so if I got rid of NA.rm, I just tried to calculate the median, it will give me NA. Then that's kind of, and the reason is because there are missing values in this vector. Because for some reason, one of these Legos wasn't sold in the United States, and so there's just an NA for that value. So, and it wasn't priced in US dollars. So by using NARM, I eliminate that data point from the data set, which an NA might be valuable depending on what data set you're looking at. But since if I am only caring about Legos that were sold in the United States, then I can remove it safely using this NARM equal to true argument to the median function. And that also applies to the mean function that I erroneously used before. Okay. And then you can, the last plot I want to talk about, I have a good one in here, is the bar plot. Bar plots are never use a bar plot when you can use a histogram if you're looking at frequency data. So if you ever have counts or frequency or anything like that, that's going to be on your y-axis. I highly recommend using hist and not using bar plot. But bar plot will sort of similarly take it will take data that has some structure. So if we just give it a vector, it will just plot each of the values in that vector as a bar, where the height of the bar is the value of each element of that vector. So not not particularly fancy. Again, bar plot has all kinds of arguments that you can add to it. The one like who knows why this is thing about bar plots is that it, instead of saying names like we said in box plot and instead of using names, it's names.arg. It does the exact same thing. It just labels each bar. I don't know why they couldn't keep those argument names consistent between functions, but things like that happen. And then the same rules apply about adding titles, adding axis labels, etc. So, any questions about this? Okay. All right, so, actually, one other thing that I wanted to cover was, so there are dozens of arguments that you can provide to these different plotting functions to manipulate them, but then the plotting window itself, you can manipulate to also do over 100 different kinds of configurations and customizations. And I'm going to go over the one that's probably most relevant to you guys, which is putting plots like next to each other. But as soon as you start playing around with these values, you can mess yourself up a little bit, which is what I think happened when I plotted that legend before, and it was huge. There are ways to go back and if you make some setting and then it causes your plots to look ugly or to look a way that you don't want them to look. The best solution I have for you is to close R and open it back up and then try to plot it again, which I didn't want to do because I was in the middle of things before. So my warning is just be kind of careful when you're making these changes. If you're in the middle of an analysis or it'll take you a long time to get to where you were in your code. But let's still, this is definitely something useful and something you should know. So this all revolves around the par function. Par takes I'm just scrolling through all of the different arguments that par can possibly take, and these arguments can have all kinds of different values, so it can get complicated. But there are many times when you want to have two different plots next to each other, and so the best way to do that is to use par, this par function. Give it. There are so many arguments, it doesn't even have auto-completion in RStudio for the arguments. So you have to specify this argument mf row, and then you can give it a numeric vector of length 2, which specifies the number of columns of graphs, the number of columns of graphs in the figure you're going to create, and then the number of rows of graphs in the figure you're going to create. And sometimes it doesn't like certain combinations, or your plotting window, which is this window, is too small, and it will give you errors about that. But there are a few that are relatively safe. So if you want to plot two graphs next to each other, um, you want one row of graphs and two columns of graphs, which is kind of strange to think about, but maybe you'll see what I mean. So I'm going to say par mf row equals this vector of 1 and 2, and then when I go to execute whatever plot functions I'm going to execute, it will plot the next two plots next to each other. So I'll say plot 1 through 10, something really simple. And as you can see, it plots like half on the left side, and then I'm going to say, hist 1 through 10 will make it a little bit more interesting, square, and then it plots a histogram on the right side. And if I, par specifies this like setting in R, so if I go to make more plots, it will continue plotting in this left and then right configuration. So if I say like plot from 20 to negative 10, it'll erase what I had before, plot on the left, and then plot on the right again. If you want to go back to plotting just one figure, you can say mf row equals this vector of 1 and then 1, and then that'll get you back to this. But not all of your settings are safe, because I ended up in that situation with a giant legend, which and the reason and I believe the reason it was giant is because I reset par this way, where if I closed R and reopened it, then the legend would be the right side. So like all looks well, but there's a possibility that you can run into some problems. Yeah.
I'm sorry, I didn't understand in R and if row.
Mm-hmm.
What was the first one and the second one? What are they individually?
Sure. So you can think of them as like the number of rows of graphs in the figure, followed by the number of columns of graphs in the figure. So for example, if I say mf row equals 2, 2, then there will be 2 rows of graphs and 2 columns of graphs. So let me see. I like the code that I used here. So yeah, so if I say par of row equals 2, 2, and then I plot these 4 graphs, first it'll plot in the upper left, then on the upper right, and the bottom left, and the bottom right. And if this was larger, it would look better. And so you're dealing with like the same settings. So if you make axis labels or you draw other lines on top of your graph, you still sort of do that in the order that you would do it anyway. But whenever you go to plot or to make a new plot, it shows up in another one of these coordinates. And then if I go back to it being 1, 1, then it's normal again. Let's try to push the limits of like 3, 3. Yeah, it'll do that for you. There you go. If you're really, I don't recommend making figures like this, but there are some circumstances where, perhaps you might want to squeeze all these things together. Does that answer your question about the rows and columns? Okay. Does everyone understand this? Okay. All right. So that covers what I wanted to say about plotting, but this is like the tip of the largest iceberg. You can go crazy drawing whatever you could imagine drawing in R. There are libraries for animating your plots. There are other plotting libraries that can just make some like really beautiful plots that are used by all kinds of journalistic organizations like The Economist and the New York Times and so have you and what have you. If you're interested in plotting in R and you want to create more of these more complicated plots, I definitely recommend checking out a library called ggplot2. I could teach a semester on ggplot2, and it's just not worth getting into like with the time that we have and the skills that I want you to come out of this class with. But our base graphics are also very powerful, and if you are trying to convey ideas, whether it be to a researcher that you're working for or your boss at work or something like that, our base graphics will definitely get the job done. And as you can see, they're relatively easy to customize. If you go Google around about this stuff, there's volumes written about it. And if you're playing around with it and you have questions, please email me about it. Okay, so we've got this like twofold use for graphs of like just exploring data sets and trying to get a sense of what's in a data set, but also communicating ideas is important. And I think that it's difficult. A lot of these plots without any context don't have a lot of meaning. So I want to talk about a way to not only put plots that you generate in R into some kind of a context, but also how to share your R code and how to put any kind of analysis you're doing in R into context. And this we'll come back around to this over the next 3 lectures, especially when we're talking about statistics and statistical functions next time. Also, I wanted to ask at the beginning of class, how many of you have taken like at least AP statistics? Like, have you or taken any college level stats? Okay. All right, so a couple of you haven't. Okay, interesting. All right. Has everyone? Can you raise your hand if you've taken Calculus 1? We will not do any calculus, I promise. Okay, great. Okay, cool. That just at least gives me a sense of your like mathematical ability. So this idea of communicating will kind of circle back around to the next 3 lectures are going to be like I will introduce a new concept and then fold it back into what we've done over the past 3 lectures, and hopefully, the course will wrap itself up nicely in that way. The way that I like to share my code and share graphs and other things that I make in R is using this type of document called an R Markdown document. Ultimately, we're here to learn programming so that we can make things, and this is one of the most valuable things I think that you can make with R. So Markdown is a completely separate. Markdown is a markup language. A markup language is kind of like a programming language, but really it's a language for specifying how you want text and figures to be translated into some kind of other document. And in the case of Markdown, it's to translate just text into web pages. So Markdown is used by a lot of different websites for quickly creating web pages, and I will link to this on the course website, GitHub, which is a website and a company. You don't really have to worry about what GitHub is, but they have a great tutorial on Markdown. And Markdown, it's just a way to sort of add annotations to text so that so that those annotations then get rendered to HTML, to web pages. So those, and the purpose of Markdown is that you can read just the plain text with the annotations by itself, and it still makes sense, even though it hasn't been rendered to a web page. So if you ever go to look at a web page, I don't know if you've ever looked at the source code for a web page, but it's totally incomprehensible. Especially, I mean, I'm a professional computer programmer, and this is basically incomprehensible garbage at first glance. There's no way to go about reading this. Where with Markdown and with our Markdown, you can look at that source code for a web page, and it's still readable. And the most immediate example I have on hand for this is this course. The entire website for this course and all of the course notes are written in R Markdown, and I've been providing links to the R Markdown without you guys really knowing what it is. But really, I want other people to be able to see what I'm doing in this course, and I wanted you guys to have lots of examples for when I talked about R Markdown. So as you can see, let me see. If you click this, it'll probably ask you to download it. Yeah. So we'll take a look at the source code for this. Okay. So these R Markdown documents automatically open up in RStudio, but I just kind of want to show it to you out of the context of RStudio. So this is the source code of this web page. So this web page is complete. Bless you. This web page is completely readable, and the source code for this web page is nearly equally as readable. And let me actually get a better example, because this web page doesn't have any R code. So if you would take a look at the, here, let's just take a look at what I did for plotting. So as you can see, this is what I would call a proper R Markdown document, where the source code is completely readable. There is a little bit of markup, for example, these backticks, or these number signs or what have you. But mostly you could go through here, and it's intuitive that here I'm just talking about whatever. This is regular prose, and then with this syntax of 3 backticks, the backtick is above your tab key, probably in between your tab and your escape key. If I specify these backticks and then I put curly braces and R inside of the curly braces, I can include R code here. And what happens is that that gets rendered in HTML to this syntax, where using those single backticks looks like code. This is larger and bolder, and where it says scatter plots, because it was preceded with 3 pound signs, and then wherever I have specified 3 backticks and this R in curly braces, it gives this. It shows up as a gray line of R code, and then it actually executes that code and includes the figure that's generated in this HTML document. So of course, there's no way to represent this image in the source code of this page, but when I render it to HTML, it's included. This is, of course, you can just create plots and export them using RStudio. But if you are, if you're ever giving a presentation or even just sending something to your boss or to your friends or your collaborators, I really recommend using R Markdown, and I'll go through making a basic R Markdown document right now. So in RStudio, you just go to New File and say R Markdown. I recommend saying that your output is HTML. The reason is you can make, if you have LaTeX installed, you can use PDFs. But if you don't know what LaTeX is, we're not going to get into it. That's also another course. And of course, I am just generally unfriendly to Word, which a lot of people aren't. But I don't know. I recommend HTML. This title and author field just gets automatically filled into the R Markdown document that you are that RStudio is going to make for you. So I'll just leave it as untitled for now. So click OK, and all of this stuff is automatically generated. This part of the R Markdown document between these 3 hyphens is just what shows up at the top of your HTML. So this is the title, this is the author, and this is the date, and then the output is just kind of like a setting that specifies what RStudio is going to turn this R Markdown document into, in this case, an HTML document. So if I just click knit HTML up here in RStudio, it'll ask me to save this document somewhere. I'm going to save it on my desktop. You'll see all of this code running, or RStudio will crash on me for no reason at all. Didn't do anything unusual. Man. I use RStudio all day, and this never happens to me. Oh wow, okay, so I don't know why that took so long. But this is, so as you can see, all this text that was just generated automatically got turned into this HTML file, and it gives you a preview of the HTML file whenever you click knit. And the HTML file the HTML file is generated wherever you saved the R Markdown file. So when I clicked knit, it asked me to save the R Markdown file somewhere. And here's the R Markdown file, and here's the HTML file that was just created. So now we'll get into the actual syntax of Markdown. There's this button after you create a new R Markdown document that just says knit HTML. Oh wait, do you have? What did you say? But what do you mean?
Like the HTML, is that what you
No, I clicked right here.
there's
Yeah. Oh, okay. Do you have that?
Yeah.
Oh, okay, great. Okay, sorry about that. Does everyone see that? Okay, all right. So if I get rid of all this and then I click knit HTML, it just gives me nothing except what I specified up here. And in fact, I think you can, if you want to, you can get rid of this. And it just will give you nothing. But I like it. So the basics of Markdown are you can specify headers, which are kind of large, bold pieces of text. One $ is the largest header. 2 is a smaller header, and I think this goes on until you get to 3 or 4 headers. Let's see. So init. So yeah, as you can see, the more pound signs I add, the smaller this gets. Then there are, then I can just write prose with no formatting or markup whatsoever. And that shows up just as normal prose, depending on the, it will be rendered depending on the settings of your web browser. I can italicize text with by surrounding it in asterisks. And I can bold text by surrounding it with 2 asterisks. And then the natural evolution of this is that by surrounding something with 3 asterisks, it will be bold and italic. 3S. There you go. You can specify, you can turn text into links using this syntax where you have 2 brackets and you write the text of the link. And then immediately following the square brackets, you write parentheses and you write the URL that you want to link to inside of those parentheses. So if I click on this, sorry, I need to say http:// so that link will take me to Hopkins' website. You can list items and it will automatically show up as bullet points. With this syntax, just using hyphens. And it'll just be bulleted for you. You can also number things and it will sort of format it nicely with this syntax of just having the number and followed by a period followed by whatever is in the list. And as you can see, that's like indented a little bit. And I'm definitely missing things. List images. Pairs and quotes. Do quotes work in our markup? Let's see. This is just a feature I don't use that often. This is a quote. Oh, interesting. Okay, so you can get this like quote syntax with a gray bar, but you only have to use one of these greater than signs. Let's see here. Yeah, so if you like that, then go for it. And probably most importantly for our purposes, before we get to that, you can also you can embed images, just things that aren't created by our code, similarly to how you can embed links. So an image, you start with an exclamation point, followed by brackets. In the brackets, you're supposed to write what's called alt text for an image. So basically, the purpose is that if someone is blind and is using a device called a screen reader to read your website, this is the text that that person will hear, and they will know that there's that it's supposed to be an image. So I'm just going to write GHU's logo, and then I'm going to link to then I'm going to link to an image. Why are you making this so hard? See, so I just grab this link, paste it in here, in those parentheses, and there it is. And then, as I started saying before, probably what's most important for our purposes is writing code and writing our code. So I can write inline code like use the plot function. These used by putting code in between these single backticks, and what that'll do, it'll make it'll make it gray around the code, and it will change the font of this little piece of code to be what's called a oh my gosh, of course I can't think of it. It's not uniform space, monospace. It's a monospace font, and which are kind of like code-ish looking fonts, like the default fonts when you're typing our code or typing in RStudio in general are monospace fonts. If you want to write a block of code, you can use 3 backticks followed by another 3 backticks, and then you put the code that you want to be rendered on the page in between those backticks. So let's get some really sweet looking code. This plot. If I knit this, then it shows up where it shows up in this rectangle. The whole thing is in a monospace font, but just putting this code in there, just putting this R code in there doesn't run the code. It just formats it in this way. So to actually run code, you use similar syntax with these 3 backticks, but after the first set of 3 backticks, you write curly braces and then the letter R. And then you can treat what is inside of those backticks as an R script that you're writing. So if I write the very simple expression 2 + 2 and then knit this document, it will show the code 2 + 2 in one of these rectangles in a monospace font, but with a gray background. And then whatever's produced in the R console will show up in a similar box, but with a white background, and it will have these 2 pound signs, and then this 1, which is what you would see on the R console, and then the value. And that goes on regardless of what expression you write inside of this R code. This R code block is how you talk about these pieces of code inside of these documents are referred to as blocks. They're also referred to as chunks. And as you can see, you've got the expression, and then whatever the result of the expression is printed immediately below it. And so, if you're plotting something, you can stick your plotting code into these code blocks, and the plots will appear in this will appear in the web pages that you're creating. So I can just plot 1 through 10, knit the document, and the plot appears. So once again, there are all kinds of settings you can get into with RStudio, and with all different ways to customize it. But as far as quickly producing documents and web pages to share about an analysis, or to share your plots in a way that you can write some explanation, have some code, and then have some plots, I really recommend using our Markdown. Does anyone have any questions about our Markdown? So actually, one other thing I want to say about it is that uh, if you want to share this privately, I wouldn't send the HTML to people. I'd open it up in a web browser and then pretend to print it and and just save it as a PDF and then send that PDF to someone. If you do want to publish this on the web and share it on the web, you can do that very quickly through services that RStudio has set up by just clicking this publish button. It's going to ask you to install some packages. I don't have like these accounts set up to do it, but RStudio makes it very straightforward, and it's hosted on their website, which I believe is called rpubs. Yeah. So you'll have to create an account here. Another website I highly recommend for sharing web pages is called neocities.org. They will just let you upload whatever HTML you want, and it's free. They give you how much is it? Yeah, you get 100 megabytes of free hosting, and you can just send people URLs so that, if you want to change something on your site, you'll have your own little website and place online. Does anyone have any questions about any of that? All the way back up to the first lecture. Okay. So I would like to do some swirl stuff with you guys now. We didn't get... has anyone worked on swirl this weekend? Or have you... Can you just say if you did work on swirl this weekend, or if you've done if you've done the functions lecture or the functions lesson, can you raise your hand? Okay. All right. I just wanted to get a sense of how far people have gotten. We spent a lot of time on functions, and if you guys have questions about functions, please ask me, but I don't necessarily want to go back to that. Let's go through some of the swirl plotting lectures, and I'll come around and I'll help you guys out. So if you run the code, if you run the following, bless you. If you do library swirl, and then install from swirl exploratory data analysis. So if you run this code, that should install the exploratory data analysis course, which is based on some of the work that I've done with Coursera.org. And let's try to do this course. If you're interested in ggplot, which I was talking about before, this course will definitely give you a foundation in that. But let's try to do the first couple lessons. Nobody go beyond lesson 5, base plotting systems. And if you guys have questions, I'm here to help. And If you finish a lesson, just let me know so that I have a sense of how the class is progressing. And we'll do this for, let's say, a half hour, and then circle back and see how we're doing.